Traditional cybersecurity focuses on the protection of digital assets, primarily aimed at preventing the unauthorized access or theft of information files. Engineering systems introduce a different set of risks, where digital breaches result in physical failure. A compromised control system can force a heavy industrial turbine to spin violently out of control until it shudders to a mechanical halt. This vulnerability was demonstrated in 2010 by the Stuxnet worm. This malicious code was engineered to cross the gap between software and hardware, specifically targeting and destroying the physical centrifuges used in Iran's nuclear program. The 2015 attack on the Ukrainian power grid further illustrated the scale of these threats. By remotely manipulating circuit breakers, attackers disconnected the electrical supply for hundreds of thousands of residents. These incidents target industrial control systems, or ICS. As shown on this control board, these environments function by integrating digital monitoring displays with manual physical switches and gauges. These breaches are often the work of advanced persistent threats, or APTs. These sophisticated, state-sponsored entities possess the resources to bypass standard perimeter security and remain embedded within a network for extended periods. Because APTs are designed to circumvent individual perimeter walls, engineering systems require an architecture that remains resilient even after an initial breach has occurred. Maintaining physical safety requires defense in depth. This approach integrates security natively into every layer of the engineering lifecycle, from the root hardware to the external network. Every physical engineering operation relies on an embedded system. This isolated motherboard is the foundational node of our architecture. These controllers operate in real time to govern critical physical processes, issuing commands to motors, valves, and power systems based on incoming sensor data. If an attacker modifies the fundamental firmware of this controller, they gain direct control over the physical machinery, bypassing safety protocols. To secure this layer, engineers utilize Trusted Platform Modules, or TPMs. This dedicated security chip is physically integrated into the motherboard. The TPM provides isolated execution for sensitive operations, like key generation and digital signatures, keeping cryptographic functions physically separate from the main processor. By establishing this hardware root of trust, we ensure the system has a secure physical foundation before any software is loaded. Scaling up from the hardware node reveals the broader system architecture. Modern engineering networks connect workstations, servers, and sensitive ICS databases across a wide topology. In a flat network, devices are visible to one another. If an attacker breaches a workstation, they have an open path to every component. We prevent this lateral movement through architectural segmentation, using boundaries to divide the network into isolated sectors. This creates a critical separation between less secure user applications and the highly sensitive databases that control industrial equipment. These boundaries are enforced by Role-Based Access Control, or RBAC, which acts as the governance mechanism for the entire network. RBAC follows the principle of least privilege, ensuring that users and devices only possess the specific permissions necessary to complete their assigned tasks.
If a standard phishing attack compromises a user workstation, the resulting infection begins to spread through the corporate sector. But because the network is segmented, the breach is contained. The malware lacks the credentials to cross the boundary into the critical control systems. Segmentation transforms a potentially catastrophic system-wide failure into a localized incident that can be identified and remediated without shutting down operations. While segmentation provides isolation, legitimate data must still cross these boundaries. Firewalls and intrusion detection systems act as the intelligent gatekeepers that evaluate every packet attempting to cross between sectors. Basic packet filtering firewalls offer limited protection, as they only inspect basic header information like IP addresses and ports, which can be easily spoofed. To meet engineering standards, we deploy stateful inspection firewalls. These firewalls track the active state and context of every connection, ensuring that incoming data is part of a verified, established request rather than an isolated, malicious packet. However, firewalls cannot always identify new threats. Signature-based intrusion detection systems are often used, but they are limited to identifying known patterns of malicious activity. Anomaly-based IDS solves this by establishing a behavioral baseline of normal network activity. If a data packet appears technically valid but behaves erratically compared to historical norms, the system flags it as a potential zero-day attack. These intelligent perimeters provide active evaluation, analyzing the behavior and intent of all internal communications. The security of the internal network is put at risk whenever remote engineers or external vendors require access from an outside location. Standard protocols like transport layer security are suitable for web traffic, but do not provide the strict access control required for industrial infrastructure. Secure remote access requires a virtual private network, or VPN, to create a dedicated encrypted tunnel through the external firewall. We use the IPsec protocol suite to secure these connections, providing a standardized framework for encrypting and authenticating all data moving through the tunnel. When operating in tunnel mode, IPsec encapsulates the entire IP packet inside a secure wrapper. This renders the data completely unreadable to anyone outside the tunnel, ensuring remote operations do not expand the system's attack surface, regardless of physical distance. This completed model represents a defense-in-depth architecture, where embedded TPMs, network segments, and intelligent firewalls work in harmony to protect the system. But even the most robust architecture will degrade over time as threat actors develop new methods of exploitation. We maintain this architecture through the NIST Risk Management Framework, a systematic process for identifying and prioritizing evolving risks. The framework requires continuous monitoring, regular vulnerability assessments, and compliance audits to ensure that every security control remains effective. Because no defense is absolute, an incident response plan is also necessary. This plan provides the exact procedures needed to contain a breach and recover operations as quickly as possible. Security by design functions as an ongoing engineering lifecycle. It requires relentless monitoring and adaptation to mathematically outpace the evolution of cyber threats.